So it's a practicals on millifluidic experiment. And I should mention that Pietro De Anna, who couldn't come in the end, is also involved. We're going to be using mostly his equipment from his lab on this experiment. So you didn't hear me. So we will use mostly Pietro De Anna's equipment, and Pietro should have been here to also supervise these practicals with us, but he couldn't come in the end. So this is a picture of the experiment. This is the last edition. Kino was already in charge of that. So the motivation of that type of experiment, which is the type of experiments that we started also with Pietro and Kino in our lab in Rennes 6 years ago. And so the motivation is that basically that in some cases what happens at really small scales impacts large scale geochemical fluxes. So there are, for example, like the clogging of geothermal fields, in situ denitrification of water, in-place stabilization of heavy metals, and so on. And then also reaction rate that can be measured on the field. When they can be measured, they're often much smaller than those measured in batch measurements, batch experiments. So we thought that it could be useful to have lab experiments with a quantitative pore scale characterization of solute dispersion, mixing, and reaction. Maybe at the expense of maybe having a bit geometries that are really far from the real system. So the experiment here is, so they are analogous experiments with a geometry that is really controlled. It's defined, it can be whatever we want. It defines, we define it by a numerical model. And it's transparent, so that we can actually measure everything at the pore scale. And so it retains, we try to have it retain a fraction of a real medium's complexity. In particular, we want it to have some disorder. And of course, the drawback is that it's 2D. Okay? So the experiment that we are going to mount here, you have the porous medium inside that flow cells, a syringe pump that is injecting the fluid and the solutes, and the camera, and we work from mostly from measurement, from optical data, from pictures basically of the medium. So what can we measure with this? We can measure velocity fields by tracking small particles, for example, or by doing PIV, particle image velocimetry. We can measure the spatial distribution of phases. Here the grains are in orange. Air is in white, and black is the liquid. We can measure solute concentration, local solute concentrations at the pore scale. So here the white is air, and blue to red is water with the concentration of the solute. It denotes the local concentration of the solute. And in some cases, we've also measured the local reaction rate at the interface between a resident fluid and an injected fluid. Okay, so we use, in that case, with an experiment that was chemiluminescent, so that each time there was a reaction, there was some photons were emitted. So here we're going to do really simple. It's going to be a conservative transport experiment.
Thanks, Yves, for the introduction. I think that the main goal is that of this practical course is what just I can speak without that.
This is for the recording.
This is for the hell of my.
This is for the video.
Can you hear me?
It's the video.
It's the video. Okay. I don't want to be famous. As Yves just mentioned, the main purpose of this practical course is just to let you know that go to the lab is not just to get beautiful images. If you are smart enough, you can get a lot of juice from the images. You can compute many, many different things. And here, those days, we're going to try to do, for example, in a saturated medium, like the ones that I'm going to present on Friday in my work, we're going to do a continuous injection, and then we're going to measure concentration field using a fluorescent tracer, in this case fluorescein. And what we can measure there is many, many different things. We can measure the interface length, we can measure dispersion, we can measure the scalar dissipation rate. If we have very nice images, we can do the derivative to compute the concentration gradients. We can compute the concentration PDF. mixing interface, many different things. Benchmarking with analytical solution, you will see if we have a very heterogeneous media like an error function or a Gaussian distribution doesn't fit the data, so it means that you have a non-Fickian transport, etc. You will see that you are able to invalidate the analytical solution. So how it will be organized in the course? It will be every day, as you know, from 10:30 to 12. This is for every practical course, and also on Saturday afternoon. And then our idea for this particular practical course is just tomorrow, Yves and I, probably with the help of one student, Mayumi Amada from Lausanne, and student of Pietro, we're going to give you an introduction about the experimental setup, about every component of the experimental setup. We're going to run an experiment for you, and we're going to give you a script in MATLAB, very simple. You can write in Python or do whatever you want, in order to analyze or post-process the images. So then, the day after, the idea is that you, by yourself, run your experiment with different flow rates, which mean different Peclet, or whatever you want. Pressure controller, flow imposed, whatever you want to do. And then after, post-process this data, and believe me, the script is very short. It means it's by yourself that you have to decide what you want to compute. Do you want to compute dispersion? Sorry, you have to write how to get this information from the images. So to conclude, because the rest has to present also the other practical courses, is that don't think that the experiments are only to validate theory. This is what we try to show in this joke. Okay? It means, of course, we need the circle of the equation of the circle, and then after we do the wheel. Believe me that also from experiment you can develop theories. So we can invert the process. That's all.